Hi, I'm Francis Alonso. I'm at my third year of Bachelor in System Engineering. I'm the electrical team lead for the past 2 years for S.O.N.I.A AUV.
Hi, my name is Kemi. I'm a graduate student in System Engineering. I've been in S.O.N.I.A for 3 years. I was the team captain last year, and now I'm the admin team leader.
With our new AUV design, we had to revisit all our sensors that were required for our submarine. These sensors include DVL, IMU, cameras, and the hydrophones. All these sensors have been integrated in this new platform, but the one we will focus on in this video is the hydrophone system. We have been working on this latest design for the past 2 years, and we will share our experience with you. The hydrophones are a vital system for the RoboSub competition, as they are the heroes of the submarine. We use the hydrophones because of the capabilities to detect the pinger signals. We must be able to detect 25, 30, 35, and 40 kilohertz if we want to go everywhere in the transdeck. The hydrophone project is composed of 3 subsystems. The first system is the hydrophone itself. We use 4 Brüel & Krager 8103 hydrophones for their ultra-compact design and the depth range that they provide. A hydrophone is composed of a piezoelectric transducer that converts the pressure change of an acoustic wave into an electrical signal. They are made to match the acoustic impedance of the water. They still work in the air, but with poor performance. To ensure a better reception of the signal, we place the hydrophones in the front of the submarine, and each one is linked to an amplifying and filtering board. The bandpass filter only keeps the frequency between 10 kHz and 55 kHz. These boards are linked to an FPGA to analyze the data with our algorithm of source location. These information are then sent to the onboard computer via USB. The hydrophones are used for the 2 tasks for the acoustic source location, usually called pingers. Both sources are located with tasks that can be completed for points. These tasks can be found without the hydrophones. The competition pool is divided in 4 parts, and each part has a different frequency, 25, 30, 35, and 40 kilohertz. To be able to test anywhere during the competition, we must make our system work for all these frequencies. Since there are 2 sources, both can be activated at the same time, and we have to make a choice at the beginning of the run to decide which one to be activated. And once the submarine has completed a task, the second one can be activated. The other option is to ask for a random pinger, where you don't know which one is activated. The random pinger adds bonus points if the submarine achieves a task at the location. We intend to use our hydrophones to complete both source location tasks with the addition of the random pinger. Just these 2 tasks can reward us with enough points to stand out. Since there's usually an object at the pinger that can be detected with our cameras, our hydrophone system was not designed with an extreme precision.
An important concept to grasp when talking about sound triangulation is that we need 2 angles, the elevation and the heading. We could only use the heading, but having the elevation and assuming the depth of the pinger will give us an idea of the distance between the submarine and the obstacle. Then, because of that distance, we are going to assume that the wavefront is a linear plane instead of a circular one. This way, the difference between the phases of the signals received on each hydrophone gives us the distance between the wave plane and the submarine. And, with some trigonometry, we can calculate the angle of incidence. With all these approximations, we know we won't have the exact location of the pinger, but we will be precise enough to put the submarine in a place where the cameras can take over the detection. If we are in an area of about 1 meter radius from the pinger, we think we can detect a task at the bottom of the pool every time, and a task in front of our submarine 2 times out of 3, after making a 360 degrees yaw rotation. We hope that after arriving at the pinger location, the detection of the task will not take more than 30 seconds of the run.
To detect the pingers, we use 4 hydrophones to get an accurate value of the heading and elevation. We use a cross-shaped pattern with an equal distance between each hydrophone to make the heading and elevation easier to calculate. We could use any other shape, but that would imply to have more sinus and cosinus formulas because the angle between each hydrophone. We used to have 3 hydrophones, and we thought that we could only use 3 hydrophones to calculate the heading and elevation, but we couldn't get an accurate value for the elevation. Also, the 35 kHz has never worked on our previous platform. We had to cut the cables of our hydrophones, and this cut has completely messed up the signal since the shield wasn't soldered properly. This time we have worked with Brüel & Krager to shorten the length of the hydrophone's cables from 6 meters to 1 meter. Another potential noise source that we found was our electronic speed controllers, or ESCs. We have now separated the ESCs and the hydrophones, so there will be less chance that we can get some noise on the 35 kHz. This is important for us since we could use more often the 35 kHz section at the competition for our testing.
We also wanted to minimize the configuration time of the hydrophone board. On AUV7, we had to program the frequency on the board before going into the water. This implied that if we wanted to go quickly in another part of the pool after a test, we could not use the hydrophones in the second test. With our new board, we can change the frequency whenever we want. Moreover, if we were to get lost in the pool, we could know our position with the pingers from the other parts of the pool. This is not a very useful feature for the competition as it stands, but if the competition were to have different frequencies in the same part of the pool, we will already be ready.
After the amplification and filtering stage, we use analog digital converters to send data to our software. Our software uses a fast Fourier transformation to recreate the hydrophone signal and detect the ping. DFFT requires a huge amount of parallel equation that can be processed on a microcontroller. This is why we use the FPGA or field programmable gate array. We are confident that the hydrophone can locate both sources at 40, 30, and 25 kHz. We're looking to test the 35 kHz, but we couldn't get any clean data at this frequency in the previous years, so we don't know how the system will react. We are sure that the random pinger can be completed, but we still need to test if the complete software architecture of our submarine can process the message from the hydrophone. The hydrophones have been primarily tested in simulation. To test the filtering and amplification stage, we use a simulation program to make sure that the right frequencies were cut with the filters. Also, we have tested the effect of different gain adjustment to validate our calculations. With these tests, we have found that our first amplification wasn't set up correctly and we were able to adjust the values accordingly. These are the only simulation made on the hardware of the project. For the software, we're able to do multiple tests. First, we had our algorithm development made on Simulink. We used the data from previous platform to characterize the signal and create a simulation of it. These tests were very useful when developing our software, but we intend to use the data from our new hydrophones to verify the functionality of the FPGA implementation. Also, we had access to a small pool to try out our hydrophones with a single hydrophone connected to the board. The pool isn't ideal since it's made of metal and there's a lot of rebound of the signal in it. We can't make the difference between the signal and the rebound. But with this simple test, we have found out some errors with our signal-to-noise ratio threshold and our signal threshold. The values set were not the values that we had thought. After adding a user entry for these values, we're now ready to test in a pool with the 4 hydrophones connected. At the real pool test, the first thing to figure out was the exact value of the threshold that we needed for the signal-to-noise ratio and the signal. We had found some issues with the data from the ADC. It seems like the data is attaining a saturation level on the charge amplifier or the bandpass filter. The next test would be to verify the accuracy of an algorithm and compare it to the simulation on Simulink with the data collected at the same time. We can't wait to go back in the water and see you at San Diego in 2022.